ready for the semester to end? Everybody? I'm sure. It's been a tough one, I think, for a lot of people. Yeah, a lot of work. All right, so once I get set up, we will be going over our review for the course, or rather continuing it. I'll be going over a lot more of those final exams that I posted for us. So again, our final exam will be on the, I believe, 8th, according to the not just the syllabus, but basically, you know, the chart of exam dates that was posted. We'll go ahead and make a paranoia check right here to make sure that we're, you know, that we've got that right. So, because I'm sure you've all had that nightmare of you registered for a class and, you know, that nightmare where you forgot that you registered for a class and you remember only on the date of the final exam, right? I'm sure you've all had that nightmare before. I had that nightmare too. The only difference is that I was registered to teach a class and I forgot all semesters. That's my version of that nightmare. So all right. So according to this, the final exams for spring 2018, which is this semester, are from May 3rd to May 9th. You have 2 study days, right? So you have 2 study days on May 1st and May 2nd. There's no classes or exams. And then from the 5th through the 9th, they are final exams only. And on the top of that, let's go ahead and let's see, screen projector preview. So on the top of that, it also says that, this is important to note, instructors are encouraged to work out individual accommodations with students who have more than 2 exams on one day. Okay? So that means that really you should not take more than 2 exams in one day.
My professor told me that they can't change an exam.
They lied.
Just today. Oh.
Well,
3 exams one day.
Yep, you can get them to change. One of them has to move. One of them has to move. Okay? One of them has to move. So one might be really adamant about not being able to move, but it says over here, instructors are encouraged to work out individual accommodations for students who have more than 2 examinations on one day. So they don't have a hard and fast rule like they do at other universities, but you are not expected to take more than. But it's if you're having trouble getting any of the 3 professors to move, talk to the dean. That's what they're there for. Okay. Okay. So right, and if you've got like special scheduling circumstances, should consult well advanced with their dean. So all right, and if for some reason you have like some kind of family emergency that happens, or you get hospitalized or something, so in that case, really the only thing, if you've been doing well in the class, the only thing we can do is an incomplete at that point. Okay. That said, those cases, incompletes require documentation. So you got to be prepared to basically give documentation for that. Okay. So if you've been hospitalized, be prepared to basically prove that you basically had an injury or something that prevented you from taking the exam. Okay. So but we really don't want an incomplete. You really don't want to try to take an incomplete because the longer you go without touching the material, the harder it is going to be. So to actually make it up. So let's see. All day and evening classes will have final exams. So please note the last page for common final exams. So because we're in evening class, we don't. Because the evening classes assume that you might have, work on during the day, we take we're going to be taking it during the evening time rather than the final exam, rather than the common final time. So 5:30 to 8 o'clock on Tuesday. I'm sorry, 5:45 to. Sorry, it's 5:45 to 7:45. So yeah. On the 8th, it says over here. So this class time on Tuesdays. The examination is on Tuesday, the 8th, from 5:45 to 7:45. So if you show up on time to our class on that Tuesday, you'll be fine, right? You'll be a bit early, and then the close off is at 7:45. You know, so that's when I'll start pestering you to finish up your exam and start handing them in. So that's what you got. And you will be taking, I think, a slightly different final than the final exam that the common students take. Okay. So again, so the average for the evening section is generally actually is about like 7 points higher than the day section. I'm not sure if it's because you're just better students or something, but like when you for the final exam, but it's still like in the 60s, like mid 60s for the average. Okay, the final exam for 2168 is brutal, but I think it just happens to be because it's a lot of content, right? You've got the time pressure, and you've got all those other exams to study for, which I think is the kicker. Oh, and it's basically been a full week since you had time to go over, actually 2 weeks since you had time to go over the material. So that also, I think, puts a damper on it. So just be aware that just because you've done well in the previous exams doesn't necessarily mean that you should take this one, super easy. So I think where we left off on this was going over the Harvard practice exam, right? But right before that, I think what I did was I went over this practice exam. Let's see, not this one, but this one, this first practice exam with the map problem, right? With the whole given user logins, right? Give me an average of the logins, right? Login times, and we showed how to do that. So there will be a map problem on the final exam for you guys. It will involve basically. I'll go into detail about the problem and actually how it's a real-world problem. But again, just remember that when you're doing maps are good at doing two things: categorizing, which was not this example, but your hangman problem, that was a good example of categorizing. And this one it's the second thing that maps are really good at, which is counting things that are counting arbitrary things. So counting user login times and counting how many times the user logged in, right? The most common type of problem is something like word count, where basically you count the number of times a word appears in the document, and you've done that a couple times on the practice exam and on the exam too. All right, so let's continue with the Harvard exam. I believe we went through this problem. We went through the police department problem. We went through the, which of these Huffman trees are valid. All right, so here's another one to just make sure we understand heaps. So an array of 7 integers is sorted by a heap sort algorithm. After the initial phase of the algorithm, which is constructing the heap, so before we actually do the whole sorting thing, which of the following is a possible ordering for the array? So if you recall, because that was like a whole week ago, which is forever, the way heap sort works is that we first transform our array, our unsorted array, into a heap, okay? And to do that, and remember, the heaps, your initial instinct might be, well, we need the smallest item to be the root, so D is the correct answer. But in heap sort, that is not the correct answer. When you do heap sort, the way you're supposed to do it is take your array or list and turn it into a max heap, right? You turn it into a max heap, which means that the root the root of the heap is bigger than its children, and every every item in the heap follows that property. So essentially, we just got to look for which is a possible of the following is a possible ordering for the array. So this is a min heap, so that's not going to work. So essentially, we got to check if these things follow the max heap property. So 85 is bigger than 78 and 45, right? So how do I find my children in the max heap? Well, we did that exercise in that for the timed lab, right? And that wasn't a particularly hard one because that one you could look up, right? Was, okay, so was twice my index plus 1 and twice my index plus 2 to find my children. Okay, and that's really all I need to rely on. Don't have to worry about it in reverse. So twice my index plus 1 and plus 2. So I'm bigger than both my children. He is bigger than both his children, but 45 is not bigger than 47 or 49, so this isn't a possible ordering. B says, okay, so I'm bigger than both my children, right? And actually, we don't have to check the first one anymore because we notice that they're all 85, which is the biggest number. So 85 is bigger than both these. 49 is bigger than both its children. 78 is bigger than both its children. And then there's no other children to check, so that's good. So 78 is bigger than 45 and 47. 49 is not bigger than, so C is not going to work. We already rolled out D, and E says, well, 85 is bigger than 51 and 78, but 51 is smaller than 53, but bigger than 49, so one of its children is bigger than it, so that's not a max heap. So the answer has to be B because it's the only valid max heap. Okay. All right, so this one's not going to be here on the test, but I'm going to review it anyway just because it's a good problem to think through. The binary search tree shown below was constructed by just repeatedly inserting items into it. Okay, which of the following input sequences is not going to construct this binary search tree? Okay, so they all start with 5 because 5 is the root. So let's see how basically this tree would be constructed. Let's look at A. 5, then add 3, then add 4, so that works. Then add 9, then add 12, then add 7, then add 8, add 6, and add 20. This is all going to work. This one works because all of them, this is a reasonable order for them to be added in, right? This is kind of the reverse of the problem that you got on exam 2, right? It was given an input sequence to draw the tree. This is given a tree. Give me the sequence that, find the sequence that does not draw this tree. So 5, 9, 3, 7, 6, 8, 4, 12, 20. That works. 5, 9, 7, 8, 6, 12, 20, 3, 4, 5, 9, now on D, 5, 9, 7, 3, 8, 12, 6, 4, and then 20, so those work. And then 5, 9, 3, 6. Okay, so there's a gap because we inserted 6, but we hadn't inserted 7 yet. So 6 came before 7, so that's not going to work. All right, so let's go ahead and answer 3 of the following 4 questions in the space provided. This one's not relevant for us because this one I worked out in class yesterday. It's just insert these into an initially empty binary tree, and it's very jagged. So sorry, it's very much a straight line essentially. And then 8, try this on a 2-3 tree, which we didn't learn. So it's not really relevant for us. This one, though, on the other hand, is, which is hashing. So suppose we're given an empty hash table of size 7. It uses open addressing, right? That's where, if there's a collision, we look for the next available space. Okay, where next available space is defined by the particular strategy we're using. So the following sequence of keys is going to be inserted: 15, 17, 8, 23, 3, and 5. Insert these keys using the following approaches. If we get an overflow, so I guess like a collision is what they mean, indicate the collision, that the element that causes the overflow. So, so here where we've got a hash table where our hash function is x mod 7, so the key mod 7, and then we're going to use linear probing to resolve that. And then this one has the same hash function, but we use quadratic probing to solve that. So let's go over the first problem, because that's something that will appear on the exam. Okay. So let me go ahead and put my indices up on the board. So we've got, right, so we've already got the table size, so we don't have to mod it, It's not really doing anything to figure out a new key. It's just modding it by the table size. So it's a pretty simple hash function. So 0, 1, 2, 3, 4, 5, 6, right? So 15 mod 7, that will give us the index that 15 is supposed to go into. So 15 mod 7 is, well, 14 is twice 7. So 15 would end up at, means that we indicate, 15 mod 7 means that we get 1, right? Remember, it's the remainder of what we divide 7 by. Sorry, of what we divide by 7. So 15 mod 7, the remainder is 1. Okay, 17 mod 7. So, well, we don't even have to do division. We can go 15, 16, 17, right, and just figure it out from there. So 15, 16, 17, right, and we'll put it over here because this is a final exam. I don't have time to waste. I'm just not going to bother doing the math. I'm going to just count now that I know where 15 ends up. Okay, now let's insert 8. 8 is, so if it was 7, we'd end up here. If it's 8, so 8 would end up here, right? That makes sense. 7 mod 8, sorry, 8 mod 7 gives us 1. So we get a collision over here because 1's already occupied. So 8 looks for the next available spot. So 8 had a collision with 1. Oh, sorry, with 15 over here. So we tell you specifically on the exam how we want you to indicate collisions. Right here, I'm just simply going to draw an arrow to say there was a collision and it was this item and this is how it got resolved. Okay. 23 mod 7. So 21 is evenly divisible. So that would give us 21 would go over here. 22, 23. So 23 goes over here, but we get a collision. So another collision. So look for the next available spot. So put 23 over here. Okay. Now to insert 3. 3 mod 7 gives us 3. Collision, collision, 3. And now let's insert 5. Oh, there's a collision there. Okay. So that's that problem. So that problem was fairly straightforward. We got it's a nice big clump of items essentially. So now for quadratic probing, how's that going to work? Well, if you anybody remember the little mention of quadratic probing that I gave? How does that work as opposed to linear probing? So linear probing defines look for the next spot in a linear sequence, right? 1 spot away, then 2 spots away, then 3 spots away, then 4 spots away. So what would quadratic probing be if that's linear probing? As opposed to looking 1, then 2, then 3, then 4. It'd be 1, then 4, then what?
8.
Not 8.
16.
Well, it's 1 squared, then 2 squared, then 3 squared, so 9 in that case. So that's what we talk about when quadratic probing. But you're getting the idea that it's separated more than 1. So quadratic probing is named because we're looking, 1 squared, then 2 squared, then 3 squared away. So 15 mod 7 gets us at the same place. So 15 goes over here, right? No collision, so we don't have to worry about quadratic probing. 17 ends up in the same place, right? Because there's no collisions. 8 ends up over here, and we look 1 squared away from where we inserted it. So it goes over here. Okay? Then we're going to insert 23. 23 gets a collision. If you remember from the last problem, it's because 21 would go over here, so 22, 23. 23, we get a collision over here. Okay, so we're going to look 1 away, okay? But that doesn't work. There's a collision there. So now we're going to look 1, 2, 3, 4 away from the original spot. From the original spot, as opposed to from the spot we collided with. It's easier to calculate it that way. So we looked 1 away, then we looked 4 away. So we're going to put 23 over here. So instead of putting a hump over there, multiple humps, I'm just going to, that makes more sense when I'm drawing that. Okay. Now when we insert 3, well, we get 1 collision over here. So 3 gets a collision over here, and we're just going to go ahead and put that over here. And then 5 gets inserted, no problem, because that spot's already open. The advantage of quadratic probing is that you end up, when you get a collision, you can end up with a lot with your hash with the items more spread out. The disadvantage is that it can take longer, both because you're not necessarily going to find the first available spot if it's really full, and the second is that also the computation itself, where we're instead of adding, for this one we're just adding and modding. For linear probing we're just adding and modding. Here we're doing adding a square, which is a multiplication operation, and modding. So we're doing addition, multiplication, and modulus as opposed to just addition and modulus. So it's also just takes like an operation slower. Okay, we didn't go over this, but there's double hashing. It's not in our book, where basically if the first hash function doesn't work, use the second hash function. Yes.
Why do you skip from going 1 straight to 4?
From here to here? With quadratic probing, you look 1 squared away, so 1 distance away. Then you look 2 squared away, which is 4. So quadratic probing, so linear probing, which is what we're going to use on the exam, you just look at 1 away, then 2 away. You look 1 step at a time. Quadratic probing looks 1 squared away, then 4 squared away, and not 1 squared, then 4 squared. 1 squared away, then 2 squared away, which is 4 spaces away. Yes?
For the exam,
linear probing, yes. Because there's not the assumption that gets covered in our classes. We don't assume that we're going to cover. It's more, linear probing is just the way that's easiest to test. So let's go ahead and do some graph problems because we did that last week, and we should totally, review those still. Okay? Graph problems. So first problem is depth first search. So that means the next problem, part B, is going to be what? Breadth first search, which means that the part C is going to be what? Dijkstra's, right? And notice that the weight of the points 4, 4, and 7. So Dijkstra's is valued a heck of a lot more than, almost twice as much as the other ones. So, we've got this graph over here. Perform a depth first traversal of the graph shown above, starting with vertex C. So then select the smallest edge first. Select the smallest edge first when appropriate. In the space below, list the vertices in the order which they're visited. So not in the order that we pop them off, but the order in which we discover them, essentially. Okay? So we're going to start at C, and what it means is select the smallest weight first, or smallest edge first. Is we're going to just, we could select. We're starting at C. In depth first search, we could go to B or E or F, right? So there's ambiguity there. So to remove ambiguity, we're always going to visit the smallest edge first, so that every student gets the same answer or same correct answer if they're right. And all the edges are not the same. So all the edges are unique, so we don't have to worry about the edge case where we're selecting 2 edges that match. So I only really need 2 data structures here as opposed to 3, but because here's my set of seen nodes, which is I'm going to start out with node C, and my stack C, and typically I would have a list of visited nodes over here. But I really don't need that because my set over here, as I write items down on it, it's going to be it's going to maintain its order, as opposed to a set on a computer. It would not maintain the order in which I saw the nodes. So this will double as my output as well, right? Okay. So the first thing we do is that we've got C on the stack. So now we look at its neighbors. So we've got B, E, and F that we could travel to. Now we want to consider the shortest weight first. Okay, which is 5, so B to C. So we've seen B, we put it on the stack. Okay, now we're at B. So let's look at my neighbors. C is a neighbor of B, but we've already seen it, so we're not going to consider it. Then we've got F, E, and A. So 13, 18, 20. 13 is the smallest, so we're going to go to A. Okay, so now we're at A. We've seen B, but we've not seen D, so we don't even have to consider weights or anything. So because D is the next place I can go. D, D. So I'm at D. I've seen both A and B already, right? So I don't have to visit them, and I'm at a dead end. So at this point, I pop, and then I look at the top of the stack to see what I visit next. So A, Have I not seen any of Nay's neighbors? Anybody new? No, nobody new to visit, so I pop. So now I'm back at, so I've recursed back, sorry, so I've traveled back to B. So let's look at B's neighbors. A and C I've already seen. E and F I have not. F is the shortest neighbor to C. So I'm gonna travel to F. Okay. And have I seen all of F's neighbors? I've seen B and I've seen C. Sorry. So yeah, I'm done with F. So I pop off F. I'm back at B. Is there still an unexplored neighbor from B? Yes, E is unexplored. So I travel to E. Okay. So now I'm at E. Pop. There's nobody else to visit. So pop off. Then I've seen all B neighbors. I'm at dead end at B, so pop off. And C has nobody new to visit, so I pop off C. So I'm done. So the order I visited stuff was CBA, DFE. So now breadth first search instead, starting at vertex C. Same rule applies though. Okay, so now we're going to visit C's neighbors, which are B, E, and F, and then visit the neighbors of the neighbors of C, which are A and D, right? And the order in which those happen depend on basically what the weights are. So we start at C. So we've got B, F. So sorry, we've got B, we've got E, and we've got F, right? D, E, F as my neighbors, right? So that's the order of C's neighbors. So I'm going to put them in B, E, and F. Oh, and right, this wasn't a stack though. For breadth first search, we use a queue instead. So we had C, we dequeued at the beginning to know where we were, and now we've added B, E, and F to the queue because those are the order of the neighbors we're going to visit. So B is next. We've got neighbors A and D, right? So we add A and then D. And that's the only thing new, right? A and D to the queue. And at that point, there's no one else to add. So we dequeue B. E has nobody new to add, so after we dequeue it, we dequeue F. It has nobody new. We dequeue A. There's nobody new. And we dequeue D. There's nobody new. Breadth first search is fairly simple. Okay. Finally, suppose we are using Dijkstra's algorithm to find the shortest path from D to vertex E. List in order. List in the order that which they become null all vertices to which the shortest path is determined in the process of solving the problem, and the length of the shortest path to E. So essentially, it's saying stop after we've discovered the shortest path to E, right? And list the nodes basically in the shortest path that you discover. Basically, that's their mechanism for making sure that you just don't like follow it. So to make sure that you actually follow the algorithm and don't just figure out what the shortest path is without using Dijkstra's algorithms. So we're going to set up Dijkstra's algorithm our way, and I'm just going to add another field to it. So we're starting from D, and we're trying to get to E. So the nodes I care about are A, B, C, E, and F, right? Don't care about D because that's my starting position. The distance to each of those nodes, the predecessors of each of the nodes, and then they care about the order in which we add them to our that we've explored them, right? So okay. So first we find out what we have to initialize everything before we start the algorithm. So we initialize by figuring D to A is 10, and D to 17 D to B is 17 distance, and everything else is infinite distance away at the beginning of the algorithm. Okay. So, and how did we get to all those places? Well, we got them all to all of them from D. Okay, so now select the first node we have to select is the one that we know the shortest distance to. 10 is less than 17, and it also happens to be less than infinity. Okay, so that's the first node that we've discovered the shortest distance to. So now now that we know that we have the shortest distance to A, let's ask if that adds any additional information. So it costs 10 to get to A. The only other node that A introduces is A to B. and which has a cost of 13. Does 10 plus 13 give us a cheaper cost? Nope, 10 plus 13 is 23, so it's not cheaper than that, so we don't update anything. Okay? So now we look for the next cheapest node. 17 versus a bunch of infinities. Well, 17 wins that fight. So we know the shortest distance to B. Okay? Now B has a bunch of other nodes and nodes. It happens to know 5. It happens to know C, F, and E. So let's go through them. B to C costs 5 more than the distance it gets to get to B. So the distance to get to B is 17 plus B to C, which is 5. So 17 plus 5 is what we're looking at. Everybody understand why how it's 17 plus 5, right? So that's 22, which happens to be less than infinity. So we say we can get to 22 now by going through B, and we can get to C now with by going through B, and the cost is 22. B to F costs 18, so 17 plus 18 to get to F. So that's 35. So it costs 35 to get to F, and we're going through B. And similar for E, 17 plus 20 to get to 37. Okay? To get to 37, so it costs 37 to get to E. And we're getting there through B. Now you might think, if you didn't study algorithm, that we're done at this point because we discovered a distance to E, but it's not. But we haven't discovered the shortest distance to E yet. We still got to continue with the algorithm. It costs 22 to get to C, so that's our next node to visit. So let's look at C. It costs 22 to get to C. Let's see if it brings any information. 30 plus C, that's 52 to get to F. That's not shorter. And 22 plus 22 to get to E, that's 44. That's not shorter. So whatever. Now F does F provide any new information? No, it does not. So finally at E, we're done. Right? Going from D to E, sorry, D to B to E, right? That's the cheapest way to get there. Yes?
How much work to reach out the exam?
You'll know how much work, but generally this is sufficient. If you're worried, you can do something like this. There should be enough room for you to do that, essentially. Cross off your previous answers as you have them, okay? So when in doubt, ask for some spare paper, attach it to your exam. When in doubt, all questions are essay questions. Yes?
Do we write infinity specifically when there's more than one step away?
We write infinity, yeah, when there's more than one step away at the beginning. When we don't know there's, right, because we're essentially adding edges to our knowledge, and we don't know about the edges that aren't connected to our starting node, right? So we're discovering new edges and asking, does that change the shortest path? Okay. All right, the other graph algorithm they have is, suppose Prim's algorithm has been executed. And I'm just going to mention this as a useful aside because it brings up an entirely new class of algorithm that we didn't go over, but it is in our textbook, and I might as well cover it now even though it's not on the exam. That way, for those of you going into 3223, this won't come as a huge shock to you. So you're welcome, I guess. So this is my options are either going over this or going over topological sort, and topological sort has an interesting problem to go with it, so I prefer to do that one. But Prim's algorithm is pretty cool because it's what we call a greeting algorithm, right? A lot of times in what we do is that when it's hard to compute the cost of something, like we've got this multi-step problem. First go here, then go here, then go here, and it's hard to compute the cost of that. A greedy algorithm says, well, planning is hard, so I'm just going to take I'm just going to make the cheapest move possible at each step, and I'm not going to care about the long-term consequences. I'm just going to make what's the best choice right now, right? I'm going to make the best short-term gain choice right now. And it turns out that actually a number of times that does produce an optimal solution. Just throwing away any long-term planning. So the classic example of where this is one of the most efficient algorithms is Prim's algorithm. Or sorry, and when I say most efficient, I mean that was the wrong term actually. Not most efficient, but where it gives you the best possible answer. So it's not necessarily the most efficient algorithm. Like, it doesn't run necessarily the most efficiently in terms of time complexity, but it does give you a correct answer in a simple way to do it. So Prim's algorithm is similar to Dijkstra's in its setup, that you have a set of nodes that that you're adding to another set of nodes, and it solves what we call the minimum spanning tree problem. So a spanning tree is a subset of a graph. Essentially, it's all the nodes in the graph and only some of the edges. The only edges you use are basically you choose edges such that there's only one edge between each vertex. So in other words, the total number of edges in the graph is b minus 1. So right, if you have if you have two nodes, you have one edge. If you have three nodes, you have two edges, right? And everything is connected. So these edges, this spanning tree has a cost, which is the sum of the weight of the edges. So the minimum spanning tree is basically creating the spanning tree with the smallest cost. And Prim's algorithm is actually fairly simple. You start out with basically S, the set of nodes in the spanning tree, and VS, the nodes that are not in the spanning tree. And you essentially have you also maintain the shortest distance as well and the source. The only difference is that basically we only contain the length of the final edge in this algorithm. And it's honestly easier to see it work in action rather than try to explain it. So essentially we start building a spanning tree from 0. And the way it works is that we're essentially going to connect one edge at a time to the connected set. So 0 is currently the connected set. And the way we do this, so here's the graph over here, original graph over here. Here's our answer as we build it for building the minimum spanning tree. Okay, so 0 is currently connected. It's the only one that's connected to our set. Everything else is unconnected. So how do we do this? Well, we're going to make the cheapest possible connection each step of the way. So, right, we can't connect 4 or 5 to 0, right? Those edges don't exist, right? 4 and 5 don't connect to 0, but 0 could be connected to 1, 2, or 3. So which of these 3 edges do we select? Well, we're going to select the cheapest possible one, which is 0 to 2. Okay? And then we just simply repeat this. So we need to connect something to the set of 0 and 2. Okay? So we can connect either 1. So we just simply look for the cheapest edge to connect. 6, 5, 5, 5, 4, 6, right? We're not going to consider 2, 3, or 5 because they're not going to add anything to the connected set. We might consider them later, though. So 5 is the cheapest thing to add because we can add it for a cost of 4. So we connect it. Then we repeat. So let's look at the costs. 6, 5, 2, 5, and 6. So 2 is the cheapest cost, so we're going to connect using 2. Now then we've got only 2 more nodes to connect. 1 and 4. So we can connect either, so our cheapest costs are 5, 6, or 6. So we're going to connect via 5. And then we have the option of connecting via connecting 1. Sorry, then now we need to connect 4. So we can connect either via 3, 6, or 5. And 3 is the cheapest choice, so we're going to connect that way. So this is the minimum spanning tree, right? And the way it works, and the reason I bring this up is that it's a fairly simple algorithm. You just simply look at all the edges that you could possibly use to connect, to add a new node to your connected set, and you choose the cheapest one, right? And now your connected set grew by 1, and now you've got to look at a bunch of new nodes. So what's cool about this is that it's a greedy algorithm. In other words, it makes greedy choices. It is going to make it looks at each step and it doesn't plan in the long term. It just simply says, what is the cheapest thing I can do right now? And it actually gives you the correct answer. It actually produces the minimum spanning tree. Now, sometimes a greedy algorithm does not produce the best answer, but it will produce but it will usually produce something that's acceptable. So they're an entire class of algorithms. So it was just worthwhile, I feel, to go over that as an aside. All right. So let's go ahead and look at some coding problems now. So we've got complete all the following problems. So this deals with binary trees. And they constructed their binary trees in a completely different way where they have an int key and an object data, kind of like a key value pair in their tree, where key is how basically things are sorted and the data is the data thing, right? Instead of doing generics and comparables, right? So I guess generics are hard or something. I don't know. But anyway, so let's look at question A. The following Java method uses recursion to find a key in a binary search tree, which uses the parameter root. It finds the key, returns the reference to the corresponding data item. If it doesn't, return null, right? This is this typical search. In this tree, find the node that the value associated with this key. So if the root is null, return null because we're at an empty tree. Otherwise, if the root has the key, return it. If the key is less than what's inside the root, then we search the left side. Otherwise, we search the right side. So in the space below, rewrite search so that it uses iteration rather than recursion, right? So with search, that's actually not too much of a problem. So let's go ahead and see what a non-recursive method would look like. So it's not too bad. We just have to basically figure out how to handle our null case. Essentially, let's just think about how this works. I'm going to start at the root, and then if it's less than the key, I'm going to go left. If it's greater, it's left for you guys. Then I'm going to go right, okay? And then left, depending on right, and depending on what the values are. And if I hit a null, I'm just going to stop and return null. So my end condition is I'm going to return null if I can't return the key. So return null down there, okay? Okay, going to return null. Next, I'm going to, but basically this whole thing is essentially the same behavior over and over again. So that's a loop. We don't know how long that loop's going to take, so it's an indeterminate loop, which means it's a while loop. While, I guess, well, root is not equal to null. While the root node still exists, and if it doesn't exist anymore, we return null. So, and then we basically do everything else. So if root kind of falls in place here. So if root has the key, if root.key is equal to the key, right? Return root.data, I believe is what they use. If key is less than root.key, in that case we're going to go to the left. Root is equal to root.left, and because this is a copy of a pointer, this doesn't really mess up the tree. It works like using current, right? And then if it's not that case, I guess I'll do an else if else over here, assuming you can spell. Else root is equal to root dot right. Otherwise, go to the right side of the tree. Right, and this will just keep iterating through the tree until we hit, a null. Now, it would be complicated if we had to backtrack during this tree at all. And if we had to backtrack, we basically would need a stack. Okay, but since we don't really need to backtrack, we can get away with just basically doing it with a while. But in general, the recursive methods are easier because you can list out your cases a bit easier. All right. So write a Java method named mirror that takes a reference to the root node and creates a new tree with its own nodes that has a mirror image of the original tree. For example, if root is a reference to the root of the tree on the left, then the return value would be a reference to the root of the tree on right below. Hint, the method is much easier if you use recursion. So public static node mirror root. So it's going to return the thing on the it's going to return the thing on the left. Sorry, it's going to return the thing on the right. So one. Oh, sorry, I didn't even. Okay. So write a Java method named mirror that takes a reference to a root node and creates a new tree with its own nodes. So in other words, don't just like move things around in the original tree. So for example, if root is a reference to the root of the tree on the left below, then the return value of mirror root would be a reference to this guy over here. Okay. So the method is much easier if you write recursion. So, okay, that actually doesn't seem too bad, right? What this has to, this is essentially, I've got to traverse this tree, right? The difference is that like I'm flipping stuff around, okay? So I got to traverse this tree. So I guess the first thing I need to do is like, if this is a tree traversal, then all the tree traversals begin the same way with the same base case, right? Never forget that. So if root equals null, I should return null. That makes sense to everybody, right? Otherwise, okay, if it's not null, well then the root of this new tree, or the root of this new subtree that I'm creating, is going to be myself, right? Right. When I call this over here, if I calling it on this, I'm going to be the root of my own tree or subtree. Now that may change, but so the root of this new subtree is going to, let's say, node new root is equal to new node. Let's see, root dot data or root dot item or whatever. Doesn't matter what you put on the exam. I'll understand what you mean, right? So new root is itself. Now I just have to figure out what my left child and right child are. Okay, and at the end of this, it says that what I need to return is the root of the new tree. So I'm going to do that. Return new root. So now I just have to figure out what my left and right child are. It's actually straightforward, which is right. I need to now flip my left side and flip my right side, right? Well, that seems hard. So what I'm going to do is I'm going to make my left child my right child and my right child my left child, and I'm going to tell them both to flip their children. That's what I'm going to do, rather than trying to figure out how to do it myself. So root. So I'll say that my left child, root dot left, is equal to mirror root dot right. Now this will work. That will work because right mirror left is going to equal. Sorry. So mirror left is on root dot right. Sorry. My left side is equal to mirror dot right. Yeah, mirror on root. Jeez, there's left and right. Okay. So what I'm doing is that I'm setting this guy's left node to the mirror of my right. So I'm just saying, and when I call mirror on this guy, it's going to create a new node with him as the root, right, and return himself. So, and I'm going to assign him to my left child, right? Everybody see how that's going to happen? Like calling mirror on this guy, it's going to, and then setting it to my left child, it's going to create a new node with 3 in it. And then I do the same thing over here for root dot right. Sorry, and it shouldn't be root dot right. It should be new root, right? Because otherwise I'm changing the original tree. And that's what we don't, and they said you don't want to do that. Root dot left. Okay? And that's all that's needed for this problem. It literally just flips around what we're, it says to my child, you're switching, I'm creating a copy of you, but on my other side, and you need to do that to both of your children. That's what it does. That makes sense? You create, right, and terminates eventually, saying, right, like when we get to 3, it's going to say, okay, create a copy of my left and a copy of my right on this side, but that happens to be null, so I'm setting null to my left and null to my right. On 2, it's going to call, it's going to say, so 1 is going to call 2 and say, you're going to be this new node's right child, and he goes, okay, right? And what he's going to do is that he's going to call mirror on root dot right, but he's going to set it as his left, and mirror on root dot left, but set it to his right. So let's see. So what is the running time of your implementation of the mirror method? Use big O notation and explain your answer briefly. Oh, I would love to be a student and get a 5-point question when asking what the running time of this algorithm is. Right? It's a traversal, right? This is the way I wrote it is a one-order traversal. It deals with myself, then my left, then my right. So it's a pre-order traversal. Well, I mean, technically, you might make the argument that's not actually any of this traversal because I technically do a right and then a left here. But I'm doing the root first, then my children. But it's a traversal, which means it goes over every single node in the tree. So, and it does it once. So it's O of n. It's a linear time algorithm, right? It's O of n because it does essentially because it's called, this algorithm is called, mirror is called once for every single node in the tree. Okay. So, supplemental practice problems. Suppose you need to maintain a collection of data whose constants are fixed. In other words, we need to search for and get items, but we never need to add or delete them. Yes?
Does it return the roots, like the node that is the first roots?
It does in the new root.
If you do like tree equals, or not, no, if this node equals this method of the tree, then it will return the first root of the node by the end of it, like when everything's done.
I'm not sure what you're saying, but yeah, if I call it on 1, it will return 1 at the end, but 1's children's will be 3 and 2 rather than 2 and 3. Does that make sense? It's going to return, right? You call root, and it's going to return new root instead of root. And new root contains, that data. And I suppose the reason they did this is that they didn't want you to mess up with doing a swap, because swaps are kind of tricky. So they wanted to basically do a weird copy operation instead. All right. So when they're asking for a collection of data, the constants are fixed, meaning we never add and remove, but we do search for an item. Okay, so we'll search for an item occasionally, but we never add and remove. Okay, it can be very large, but you can assume it fits into computer memory. Which of the data structures is the best one for the task? So a sorted array. So we need to add and remove. So not adding and removing to it. So let's just think about the time to search for something in a sorted list. The sorted list to search for something. That's what? To search for something in a sorted array. Yes. Log n time because we can do binary search. That's pretty good. Searching for something in a linked list. How long is it going to take to search for something in a linked list? O of n. Linked lists are terrible for searching things. That's probably not a good answer. Great for adding or removing things on the end, but that's exactly the opposite of the problem we want. Binary search tree. Assuming it's balanced, log of n time, right? To do anything in that. It's kind of the perfect jack of all trades when it comes to data structures. The cost, of course, is that you have to have additional references. You have to have 3 references, 1 for the data, and 2 for the thing, and 2 for your left and right child. And for a sorted array, you need just 1 reference, which is to the data. A queue. That's not going to work because you can only look at 1 item in a queue, right? The front. So you can't ever search a queue. You can't search a queue. At least if we're using it as a proper queue, right? You can do O of n retrieval of the first item and O of n adding to the end. So O of 1 adding to the end, but that's about it. So Q is not at all suited for this problem at all. E says all of the above perform the same in this case. Well, D we just simply say is just completely an invalid thing for the problem. It's not even, forget big O notation. D is just not going to plain work for this application, right? So E, as a result, is wrong as well. So we have to choose between A, B, and C. Well, B was O of n, and the other two were O of log of n. So we're going to toss out B because it isn't the most efficient thing. And then a sorted array, this is actually a good use case for it because we're not going to add anything to it. If it was a sorted array, it'd be terrible because we have to shift stuff over in a sorted array. But if the array is just coming to us, it's going to stay fixed and it's sorted, we don't have to worry about it. So that's going to be more memory efficient. Okay. So number 2 is just useful because I'm assuming that the students didn't come into this knowing Java. They might have started with a simpler programming language like Python, and then this might have been the first 3 weeks of their data structures course might have been learning Java. Because this question's a fairly good 1068 question. I might send it to Dr. Fiore. Given an array of integers shown below, okay, 5, 19, 6, 12, and then blah, 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 because if we look at the problem, we only deal with indices 3 and 2 for this entire problem. What is the output of the following statement? Int a2 is equal to array. Take the value in 2, stored in 3, take the value in 3, stored in 2, take the value in a2, 3, stored in array of 3, print out the values. Well, this is just a bunch of do about nothing, okay? Because here, int array 2 is equal to array, that doesn't copy the contents of array into a new array called array2. What it does is it sets up an alias. Array2 and array both reference this array right now, okay? They're the same array. We're not, right? What are we doing? What, right? Equals copies the memory location on the right, or it copies the value on the right, which is a memory location for any object, and stores it in the variable on the left. Okay, so now we're saying take the thing at index 2 and copy it into index 3. So now they both hold 6. Now take the thing in, right? So the fact that it's array versus array 2 doesn't matter. Take the thing, take 6 over here, copy it into here. Now they both have 6. Copy 6 over and overwrite 6. Copy 6 and overwrite 6. Print out 6 and 6. Right? So that problem's only hard if you forget how aliasing works. It's one of those that's a good review problem for that. So let's see. I think that's all we really. The last problem is the only thing I feel is relevant. Which of the following sorting algorithms does not require a quadratic number of steps in the worst case? Okay, so insertion sort, what's its worst case scenario? What's the runtime in its worst case scenario? It's O of n squared, right? Insertion sort in the worst case is O of n squared. Selection sort is O of n squared always. Heap sort is worst case scenario is what? It takes O of n time to build a heap, and then it takes log n as n log n time to remove. Then it takes log n time to remove an individual item from the heap, and then you have to do that n time, so it's n log n for heap sort. So it's n plus n log n for heap sort, just n log n. Bubble sort is O of n squared. Quick sort, though, what's its worst case scenario? Quick sort, right, if we get unlucky with our pivots, right? If we get unlucky with our pivots, even though on average quick sort is n log n, right? Because it's going to keep, because with quick sort we split it in half a bunch of times. Worst case scenario, we don't actually split it in half. We're splitting it into one node and the rest of the nodes. So worst case scenario, quick sort is O of n squared. So heap sort is the only thing in this list. Only heap sort and merge sort, as algorithms that we have learned, always run in n log n time. The cost is that heap sort requires you to actually, you have to have basically an array-based structure for doing it, right? And you have to, and it requires a bit of time to build the heap, but otherwise it's super quick. Okay. And then there's some weird other stuff you can do with the heap sort, like you can sort small subsections of the array instead, which is pretty cool. And merge sort, its cost is if you're doing an array-based data structure, it costs O of n extra space to do it. It always runs in n log n time, so merge sort's always super quick. But it requires extra space unless you're using linked lists, because linked lists you can just move around the pointers. All right, so that's the Harvard exam, and it wasn't too bad, was it? That was a practice exam, not too bad. So let's see. When we went over a bit of this one, with hash tables. Suppose we have a hash. So here's another good hash table function. Suppose you have a hash table and you insert some elements into it. When you inspect, so this is a hash table that's using chaining, by the way. Okay, meaning that each item is a linked list. Okay, so when you inspect it, you see the result is it looks like the picture below. Being a good student, you realize there's a problem. So what is the problem?
Space.
Sorry?
Space.
Space? What, elaborate.
There's gaps in between.
There's a lot of gaps. This is a hash table that uses chaining, which means that basically if you get the same hash function, right, things end up at the same. If two things collide, you just simply chain them together into a linked list. And here we've got a lot of empty spaces, right? A whole lot of empty spaces. Are there any? Oh, let's look at. Is there any like kind of pattern we can see about what spaces are filled and what spaces aren't filled? Yeah. Only the even spaces are getting filled. Now, that may just be a coincidence, but I'm inclined not to believe that's a coincidence, right? And the odd spaces are not getting used. So part 2 is, what is an example of a hash function that could give rise to this behavior, right? What's a hash function that could? So we see that 30 ends at 0. So 0 and 30 end up in index 0. So 21, 31, and 1 end up at index 2. 4 ends up at index 2. Sorry, 2 ends up at index 4. So 3's end up at index. So what's going on here? Take about 2 minutes to try to figure out the answer to yourself. What is a possible hash? Construct a function that basically results in this behavior. So think about this for like 2 minutes. What is a hash function that results in items ending up, in spaces like this? Any suggestions? Yes.
The last digit, like half of the space.
So yeah.
0 is half of 0, and 1 is half of 2.
Right. So in this case, though, that's a pretty good answer. So what we're doing here is that we're taking a look at the last digit. What I would say this hash function is actually right? Because we want to create a mathematical function out of this. It is, right, so h of x, in this case, for that, an h of x that could give us this. It doesn't, we can't like prove that this is the one unless we like, but this is one possible answer, I would think, is to do x mod 10 to get the last digit, right? And then multiply that by 2. So mod by 10 to get the last digit, right? Last digit multiplied by 2, that's the index we want to store it in, right? So that's why your index 6s are stored at 12s and your index 8s are stored at 16s. So, what would be a better hash function? Almost anything else that you put down would be a better hash function. So first, just even a better hash function, mod by the table length, which is not great, but hey, it's better than that. Modding by 20 is a better hash function. Modding by the length of the table gets you a better hash function, right? All right, so let's go ahead and okay. Let's go ahead and see. Oh, I like this first problem. Okay, problem 7. Suppose that we first insert an element x into a binary search tree that does not already contain x. Okay, so we say we insert 14 into the tree, and it doesn't already have 14. Okay, that's what I always like to do when I see like letters like x. Sometimes it just putting in an example makes it more real. So suppose I insert an element 14 into a binary search tree that does not already have 14. Suppose then we immediately delete 14 from the tree. Will the new tree be identical to the original tree? Right? Sorry. Will the new tree be identical to the original one? If yes, give a reason in no more than 3 sentences. If no, give a counterexample. Draw pictures if necessary. So let's think about this. Now this is a binary search tree. Nothing about self-balancing, right? If it's self-balancing, all bets are off. We can simply say no, counterexample. Counterexample. I inserted this into the tree. It rotated. Now the new node I just inserted is now the root of the tree, right? And now I deleted it, which deletes the root, which now messes up my tree. Okay. But this is a regular binary search tree, so when we add something, where does it go? When we add something to a tree, it goes to the bottom of the tree, right? It looks for the first empty leaf that we can find, right? It travels to a leaf, and then it becomes the child of a leaf node, right? So when we add a node, it becomes a node so when we add an item, when we immediately add it, it becomes a node with no children, right? So it's going to look something like this, right? So it could go like over here, okay? And then if we immediately delete it, right? That's the easy case. That's the super easy case of deletion, right? There's nothing to change for it because it has no children. So if we immediately add something, then immediately delete it, it's going to be as though it was never there in the first place, right? Assuming it doesn't self-balance, right? Because it's going to be, why is it never going to change anything? Because it's already at the bottom of the tree. And, well, what if there was a duplicate? Well, our question says we don't have to care about that. It's not already in the tree, so we don't have to worry about there being a duplicate, like, at the root or something. Okay. Let's see. So, let's see. Suppose you have a graph like this one. The dot signifies some part of the graph you don't know exactly. Not a straight link. You also know that, however, there are many paths from the start to the goal. You also know that they tend to be rather long. Suppose you want to implement a program that searches for a path and returns the first one it can find. You don't need to find, you have no need for finding the optimal path in any sense. Just any path will do. Do you want to use depth first search or breadth first search as the basis? Remember, we use depth first search and breadth first search. So justify your answer whether you use depth first search and breadth first search. So which is better for this use case? Right? We haven't really gone into that too much, but let's think about that. Yes? Okay. So just justify your answer. Because I would choose breadth research, but that's because I'm biased toward this kind of, because I'm kind of biased towards one answer versus another. But I want to know why depth research.
Because you know you're going to hit at least the farthest point or the bottom point of that.
Okay, so you know that basically with depth search that, so this is assuming that there are many paths from the start to the goal. Right, so this sets up kind of the assumption that basically you go over here and then there's many paths, but there's a straight line you can follow, essentially, right?
Right.
Right, and if we're working under that assumption, then yeah, depth first search will get you an answer. It may be the longest. You might accidentally choose the longest route, but there will be a route, right? And the assumption I'm working with, okay, because I don't know what's in this professor's head, right? Because the professor normally, this normally isn't the first occurrence of a problem when they get something like this. This is sometimes something else. I'm thinking like along the lines is that, you know, I could go here and there's many branches, right? In that case, I wouldn't want to use depth first search if there's many branches. If we're operating with your assumption that basically there's like maybe 20 nodes between here and there, but this is like a direct base like a graph. You know, 20 nodes from here to there, 10 over here, 13 over here, 2 over here, and we just choose one of them. That's going to get us a path. Yeah, that's a perfectly valid answer for under those assumptions. My assumption is that basically that each of those branches, because I'm like viewing this as like the 6 degrees of Kevin Bacon game. Like this is me, this is Kevin Bacon, I want to get in, right? So in that case, like I would go with like, and that's because I'm biased because of the research I have to do, right? I did research in small world networks, which basically very interesting example, very interesting experiment by a guy named Stanley Milgram. Anybody know him? Anybody hear of the Milgram shock experiment, where the reason now you have to get reviews on what experiments you want to perform on people? Okay, for those of you who don't know, he was essentially he watched the Adolf Eichmann trial. Anybody know who Adolf Eichmann is? One of the main perpetrators of the Holocaust, right? He escaped to South America, was captured, and was tried in Israel, and he watched that trial, and basically, he gave the line essentially of just following orders. So being a psychologist, Milgram was like, oh, so is that a valid thing? Do people just follow orders? And Milgram says if you've got somebody in an authoritative speaking voice, an authoritative speaking uniform behind you, his experiment says, in fact, yes, they do. But it really depends. At least his original experiment was. Other experiments that replicated and try switching the variables show different things. Okay, so his experiment was I'm going to recruit people, and we're going to have an actor essentially. Okay, so I've got my experiment person and the actor, and they're essentially one of them is going to take the role of basically being the learner, and the other is going to be the teacher. That's the role, the teacher and the learner. And they rig it so that the actor is always the learner, and the person the experimentee, the subject of the experiment, is the teacher. Now you don't know this is an actor, right? This is just an actor pretending to be another experimenter. So they set them up in a different room, and they simply say, so when the person, you're going to ask them questions, when they get the question wrong, hit this button, it's going to give them a shock. Okay? And then we're going to go and increase the voltage every time they get it wrong. Now, of course, this is all fake. The guy is it's not hooked up into anything. He can't really scheme anything, but you can hear the guy screaming in pain when you hit the button. So the question was, how many people go all the way to the meter marked death? A depressing number of people is the answer. Some people, of course, would refuse, essentially, and that was kind of the experiment. There would be a guy with a clipboard saying, basically, they'd hold a clipboard, and they would say, essentially, they had 4 canned lines, essentially, that basically, you must go on, the experiment must continue, hit that button, this is, it's essential that you continue. It's something along those lines. They had 4 lines. After the 4th time, essentially, they would, if the subject refused to hit the button anymore, the experiment was ended. It was a track of how far people would go, essentially. A depressing number of people, did did not do that. A good number of people did stop before the end, but it's still a depressing number of people who continued. I don't know what the exact results are. You can look up the Milgram experiment. It's kind of horrific because, of course, you can imagine the psychological damage to a person who just thought he engaged in an experiment that killed someone. So anyway, that was what Milgram is known for. His other experiment is stuff that was relevant to my research. But his other experiment was on small world networks. It's kind of the idea of like, if you're from New York, oh, do you know Judy in New York? Of course I know Judy in New York. She lives, 2 blocks down from me. And basically, you've had some variation of that experience in your life, right? And so kind of the idea here was it was kind of an experiment to find out the degree of connectiveness that people have. So it was a fairly much more mundane experiment. What they did is that they selected some random stockbroker in Boston, right? They recruited a stockbroker in Boston. And simply, they had this guy, they listed his profession, essentially, and that the city he was located in, okay? Or the general area or something. And then they recruited people in Kansas by, mail for this experiment. And the people they recruited, they gave them a packet of envelopes, and they said, if you know this person, send him mail. Send the mail directly to him. If you don't know this person, take these instructions with the rest of the envelopes, pack it into an envelope, and now send this packet of envelopes to the person you feel who's most likely to get this letter to the next leg of the branch. Now the question was, how many legs does it take to get to this person? And for the people who were able to eventually complete this, on average, it was a big hump essentially around 6 people. Basically 6 degrees of, so that basically that's where the idea of 6 degrees of separation comes from. The bell curve was kind of settled around 6 for the people who completed that. Basically it would take about 6 hops, 6 forwards to get from Kansas to this random person, right? Because essentially it would go something like this. Like, I don't necessarily know somebody who lives in Boston, but I can forward this to my cousin George, who I know who works in, maybe Chicago. And Chicago's a big city, so he might know somebody in another big city, right? And so George might not know that, and I not know somebody who worked in New York, but he might know somebody who's worked with somebody who worked in New York. Send it to them, they send it the rest of the way into New York, and somebody in New York does the same thing for Boston, and then, oh, well, he's in accounting, so we can send it to an accountant in Boston that I know, and then that community gets smaller and smaller. So you can see how basically it just narrows down on that. So I kind of sidetracked you with a nice, amusing story. But in that kind of case, where I would use breadth first in this case. And what I would do is that I would actually do it, because it's a huge graph, in my opinion, like on a social network graph, I would start this way and then go this way. Right, I basically do breadth first search from 2 ends. I do breadth first search, search this neighbor, then search this neighbor, okay? Then I search the neighbors of here, and the neighbors of here. And now I search basically for, I search for the distance 4 in one direction, and I search for the distance 4 in another direction, okay? And then I can do that, and then I can continue doing that until I hit some kind of, intersection, right? Until I encounter the same node. The advantage here is that I'm probably actually going to find the shortest path. Disadvantage here is that my memory costs are going to be ginormous. I'm going to have 2 massive queues, essentially, of nodes. So there's an argument where depth first search, right, if you're winding, that depth first search has the argument, you can. The issue with depth first search is that you can go down a windy thing and hit a dead end and then have to back up. But if the assumptions are that these are straight line like connections here of random length, then depth first search is the way to go. So, all right, I think that calls for a small break, and then we'll get back to answering more questions.